Hello, so let's take a look at some NMR spectroscopy and start with the basics on proton resonance. So we have certain isotopes like hydrogen and carbon-13 which create their own magnetic field around the nucleus because we have either an odd number of protons or an odd mass number. And of course in that nucleus we've got positively charged particles of protons, and with that spin on the nucleus we create that magnetic field. A magnetic field around the nucleus of these atoms which has a magnetic moment, a direction of propagation. So if you apply an external magnetic field to that sample, basically put your organic sample inside a magnetic field from a magnet, you'll find that some of these nuclei have a magnetic moment which is aligned with the external magnetic field, which we represent with B0 here, from the bottom of the page towards the top. And some of the nuclei have a magnetic moment which is aligned against the external magnetic field, pointing straight down the page. So we can flip these nuclei which are aligned with the external magnetic field, flip them to have the magnetic field and that magnetic moment aligned against the external magnetic field by hitting the nuclei with the correct energy of radio frequency radiation. And when this happens, the remaining nuclei all flip to being aligned against the external magnetic field. Remember, we're assuming the external magnetic field is coming from the bottom of the page towards the top. And so we get these nuclei, as they flip, to come into resonance. They'll eventually lose that energy and return back to the original state, aligned with the external magnetic field. And as they do that and give off that energy, that emitted energy is detected and we get a signal. Usually, when we put a sample into a magnetic field, about 50% of the nuclei have a magnetic moment which is aligned with the external magnetic field, and about 50% aligned already against the external magnetic field. But when we hit the nuclei with the correct energy to bridge that energy gap to the higher state, aligned against the external magnetic field, that's what we call coming into resonance. So we're going to be thinking about the energy that it takes to flip each nuclei from being aligned with the external field to being aligned against the external magnetic field. That can change depending on how strong the external magnetic field is. If we increase the strength of the external magnetic field, we increase the energy gap between the two states. However, sometimes it's other factors which are at work which cause the nuclei to feel a different kind of field strength. Whatever the actual external magnetic field B0 is, they could be feeling an external magnetic field which is greater or less than the original external magnetic field. There's a couple of reasons for this, but one of the main reasons is the electrons which surround the hydrogen and carbon-13 nuclei. Just like the hydrogen nucleus itself, the electrons have charge and they also have spin and movement. So the electrons in chemical bonds create their own magnetic field. And this is what we sometimes refer to as the localized magnetic field. So this is a separate magnetic field from the hydrogen nucleus himself and the external magnetic field which is being applied to the nuclei. So if we look at, for example, a sigma bond, and here's the magnetic field being produced by the electrons in the sigma bond to the hydrogen atom. So we're normally talking about a carbon to hydrogen bond here. The local field produced by the electrons as it hits the hydrogen nucleus is actually aligned against the external magnetic field. So again, our external field coming up the page, and that localized field, as it comes across the nucleus, it's working against the external magnetic field B0. And so the field strength felt here by the hydrogen nucleus is diminished. Think of it like the currents of a river. If the current is moving from the bottom to the top of the page, and there's a separate current butting heads against that main current, then the effective field strength felt here is less than the external magnetic field on its own. So the electrons in that sigma bond, that localized field, is subtracting from the external magnetic field, and the effective field felt is diminished. So if we think about the energy it would need for a nucleus, a hydrogen proton nucleus, to be flipped from the low energy state into the high energy state, if it's diminishing the strength of the external magnetic field that it actually feels, we're moving to a lower energy effectively, and so that energy gap between the low state and the high state diminishes. It would take radio frequency energy of lower frequency to get the proton nucleus to flip. However, there are other chemical bonds not directly attached to the hydrogen which will also have some influence on the hydrogen nuclei. If there are polar covalent bonds nearby with more electronegative atoms than carbon, of course the electrons in that polarized bond are being pulled away from the carbon. So electrons pull towards the oxygen or nitrogen or a halogen like bromine. And so the carbon atom each time feels electron deficient. Of course, the carbon has a greater electronegativity than the hydrogens it's bonded to. And so feeling electron deficient, the carbon in turn draws electrons away from the hydrogens in those sigma bonds. That effective thinning of the electron density around the hydrogen nucleus has a detrimental effect on the local field, which we said was protecting the hydrogen nucleus. So that subtracting effect from the localized field working against the external magnetic field, B0, if that effect is being diminished, then the effective field strength felt by the hydrogen nucleus increases once more. And so the energy increase means that we get a bigger gap in energy between that low energy state when the magnetic field of the hydrogen nucleus is aligned with the external. That gap to the state where it's aligned against increases. So it's going to take radio frequency energy of greater frequency to get the hydrogen nucleus to flip and come into resonance. We also have an effect from double and triple bonds. If we think about double bonds in an alkene for a second, think about them alongside an aromatic ring with an extended conjugated system around the carbon ring. We look at the magnetic field produced by these pi electrons, and as it hits the hydrogen nucleus, for both the double bond and the aromatic ring, these localized magnetic fields are working with the external magnetic field. So the external magnetic field is strengthened by these localized fields, and the hydrogen nucleus feels a magnetic field which is stronger than just the external magnetic field alone. The external and the localized fields combining. And this is what we sometimes refer to as de-shielding. So the external magnetic field is working with that local field from the pi electrons, and so the hydrogen nuclei feel a local field strength, or feel an effective field which is stronger than just the external magnetic field alone. And so just as we saw with the polar bonds being nearby, the energy gap between being aligned with to being aligned against, that energy gap increases, and it's going to require greater radio frequency energy once more. So if we switch to a triple bond between two carbon atoms and look at the localized field produced by the pi electrons this time, as a magnetic field from the pi electrons, as it hits the hydrogen nucleus now, it's now working against the external magnetic field again. It's trying to diminish the external magnetic field, and so it's protecting the hydrogen nucleus once more from the external magnetic field. Whenever this happens, we refer to it as a shielding effect. And so now that energy field felt, that magnetic field felt by the hydrogen nucleus, is smaller than the external magnetic field alone, because the localized field from the pi electrons is working against the external magnetic field. And so the field strength felt is diminished, and that gap in energy between the two states for the hydrogen nucleus is diminished once more. Now, different NMR machines use different magnetic field strengths for the external magnetic field, and sometimes use different strengths or energies for the radio frequency energy being used to flip the protons. And so we could have very different spectra from one machine compared to another if we don't use a standard. And that standard reference for all NMR spectra is tetramethylsilane, TMS. Now the reason we use TMS as the standard is because all 12 hydrogens, all 12 protons, are equivalent to each other. They have exactly the same environment. Each hydrogen is on a carbon connected to another two hydrogens, which is in turn connected to the silicon, which is in turn connected to the other three methyl groups. So the same environment, so there should be just one signal for a sample of tetramethylsilane. But the carbon to silicon bond itself is polarized in favor of the carbon. We've got a greater electronegativity for carbon compared to silicon, 2.5 compared to 1.8. So the electrons are polarized towards the carbon each time, making the carbon electron enriched. And so the surrounding carbon to hydrogen bonds get a bigger slice of the electron density in those carbon to hydrogen bonds. That increase in electron density around each hydrogen nucleus means that the shielding effect that we talked about for the sigma bond is increased. And so the hydrogens for tetramethylsilane are just about, with just a couple of exceptions, the most shielded hydrogens we can see in NMR. So when we look at an NMR spectra, our 0 starts on the right hand side, where we have the sample of tetramethylsilane showing up with its peak. Now in most spectra you'll see for a compound that signal for the TMS is erased, but at 0 that's where the TMS is coming up. And remember, as we look at the NMR spectra, going from left to right or right to left, moving from left to right, we say that we're moving upfield. And moving from right to left, we say that we're moving downfield. The further upfield we go, the more shielded the hydrogen nuclei are, and the further downfield we go, the more deshielded the hydrogen nuclei are. Remember that relative amount of shielding or deshielding depends on how much energy is felt at the hydrogen nucleus. So with the tetramethylsilane upfield at 0, that's some of our most shielded hydrogens. And so the effective field strength that they feel is at its relative lowest point, because the surrounding electrons and the magnetic field produced by those electrons is diminishing the field strength felt from the external magnetic field. But as we move downfield to the left, we start to see increasingly more deshielding, and that deshielding, as the localized field eventually works together with the external magnetic field, creates a field strength at the nucleus which feels stronger than just the external magnetic field alone, and so we're getting a bigger energy gap and needing higher energy radio frequency radiation to flip the proton into resonance. Just to finish off, if we look at some examples, so tetramethylsilane is the most protected, it's the furthest upfield. Still fairly high upfield would be hydrogens attached to a carbon-to-carbon triple bond, because as we said, that localized field produced by the pi electrons is also a shielding effect. The localized field is working against the external magnetic field, but it isn't shielding as strongly as tetramethylsilane itself. So comparatively, it's a little bit downfield. We move on to a hydrogen connected to a pi bond, a double bond. The magnetic field produced by those pi electrons is working with the external magnetic field and is therefore a deshielding effect. That deshielding effect is stronger when the hydrogen is connected to an aromatic ring. We're talking about more pi electrons after all, producing that magnetic field. And then for a hydrogen on an aldehyde, we've got that deshielding effect of the pi electrons and the carbon to oxygen bond next door, but we've also got the electron withdrawing effect as well, which withdraws and removes electron density away from the hydrogen nucleus in that hydrogen to carbon bond.